Hello and welcome to this next video for Topic 4. In this Part 3 of Topic 4, we will look at how to compute z-scores or standardized scores and how to compute probabilities on probability density curves using tables. So let's start with a quick introduction. We have already seen data sets such as data sets that deal with the length of human feet or the length of pregnancies, lots of data sets where the distribution follows a nice bell shape, bulges in the middle and tapers off at the end, and you can see a picture of this here in the lower right hand corner. So what does the symmetry mean? In a case like this, symmetry tells us that the variable is just as likely to take a value a certain distance below its mean as it is to take a value that same distance above its mean. So values that take place over here on the right side of the mean are just as likely to happen over here on the left side of the mean. The bell shape indicates that values that are closer to the mean are more likely, and it becomes increasingly likely to take values far from the mean in either direction. So what the bell shape is telling us here, where the bell here is bulging here in the middle, is that we have quite a few of our values for a random variable that can take place right here in this region, but over here, as the shape of the curve tapers off, you have very few values of the random variable that are going to take place out here on either this edge or over here on this edge, or in what we call the tails. We call this the normal curve, and this comes from the history of how statistics was developed in the early 19th century. When they were first developed, they were called normal as a way of suggesting their depiction of a common and natural pattern. Now, we shouldn't think that there's just one normal curve. There are actually many normal curves. Here are just a few that we can look at to see if we can compare and contrast them. There are many normal distributions, and what's important to remember is that they vary in their center and they vary in their spread. That means that the mean, or mu, which is this symbol right here, and the standard deviation, sigma, are what help to distinguish normal curves from each other. Let's look at some similarities and differences on this set of curves here. If we focus just right now on the red and the black curve, which are right here in the middle, we notice that they have the same mean, which is 10, so they're centered at the same point at the mean. However, they have a different standard deviation. You can see that the black curve is not nearly as spread out as the red curve, and so therefore the black curve has a smaller standard deviation than the red curve. The more spread out it is, the larger the standard deviation, as we have seen before. If you now look at the black and the green curves, which are these two taller curves here, you'll notice that they have different means. The black curve has a mean of 10. The green curve has a mean of 15. However, they're the same width. You can see basically that they have the same standard variation. So the spread is basically the same. And then finally, if we look at the red and the green curves, this one here that's a little shorter and this one here over to the right, we can see that not only do they have different means at 10 and 15 respectively, but they also have different standard deviations. So just again to point out, there are many normal curves and they vary based on their mean and their standard deviation. The next thing we want to look at here is the standard deviation rule. This has many names. Sometimes it's called the empirical rule, sometimes it's called the 68, 95, 99.7 rule. We've seen this before, but it also applies to these normal curves that we've just been talking about. So if x is a normal random variable, then we know that 68% of the values of that variable will be within one standard deviation of the mean, 95% will be within two standard deviations, and 99.7% will be within three standard deviations. Visually, it's going to look something like this. Here's a picture of a normal curve. You can see here, mu, the mean, is here at the center. And then on the horizontal axis, you see one standard deviation away from the mean marked to the right, and one standard deviation from the mean marked to the left. And so here, up here, this is telling us that 68% of the values of this random variable here will take place within one standard deviation of the mean, and then we can mark this out within 2 standard deviations, moving from this left side here over to this left side here. 95% occur here, and then upwards, as you can imagine, 99.7% occur within 3 standard deviations of the mean. Meaning, of course, that if you go out, if you subtract 3 standard deviations from mu, which is in the center, and add 3 standard deviations, then virtually all of your values for the random variable live right here. You can also look at this from a different perspective. Notice that the information from the rule can be interpreted from the perspective of the tails of the normal curve. So over here on the left, when we have this situation where we're looking at 1 standard deviation away from the mean, we know that 68% of the values occur right here. That leaves a total of 32% of the values that are outside that region, and because of symmetry, we know that exactly 16% will be over here on the right and 16% will be on the left. So each tail has 16% when we're 1 standard deviation away from the mean. And the same can be described for 2 deviations away from the mean. In this case, 95% are within 2 standard deviations, leaving 5% for the tails. And that means that 2.5%, or 0.025, is reserved for each of the left tail and the right tail. And the same would happen for being 3 deviations away from the mean. But then in that case, you have very small percentages of the values out here in the tails. In fact, this is less than 0.2%. So we're looking at about 0.15% of the values on either end of the tail if you're 3 standard deviations away from the mean. This particular perspective will be helpful later in the course, but just to mention it here, it's important to realize that there's different ways to view these probabilities. Now, this particular rule works really well if you've got very well behaved data points that are exactly 1, 2, or 3 standard deviations away from the mean. But in reality, we normally don't have that case, and so pardon the pun there. Here's an example of what I mean by that. Let's say we're looking at the Gary Tire Company, which has developed a new steel-belted radial tire. Managers for the company believe that the mileage guarantee that they plan to offer with that tire is going to be an important selling point for their company. However, before they want to finalize the warranty details and policies, they do a few road tests to gather some data. So let's say that X is the random variable that describes the number of miles that a tire lasts before it fails. The data that they find indicates that the mean number of miles before failure is 36,500, the standard deviation is 5,000, and this particular random variable behaves according to a normal distribution. So those are the parameters. Now, management wants to know what percent of tires can reasonably expected to last more than 40,000 miles. In other words, what is the probability that the mileage for a given tire will be greater than 40,000? Now, keep in mind, if we know, as we do, that the mean is 36,500 and the standard deviation is 5,000, then 1 standard deviation above that mean would be 41,500 miles, not 40,000, which is what we are interested in. So because of this, we can't use the 68, 95, 99.7 rule because we are not exactly 1, 2, or 3 deviations away from the mean. Let's take a look at what this means in terms of a picture. We're asking the question, what's the probability that the mileage will be greater than 40,000? So if we look at the picture here, this is the curve that describes this random variable. Our mean miles until failure is right here at 36,500, and then we see here, this is the mark that we're interested in, 40,000 miles. What we want to know is, what is the probability that a tire will be in this region here? What is the probability that X, our random variable, will be greater than or equal to 40,000? That probability, as we've seen before, corresponds to the area here of this dark blue shaded region. If we were interested in the probability that a tire lasted less than 40,000 miles, it would be over here in this lightly shaded region. So you can see here that if we want to ask this question, we would need to be able to figure out what the probabilities are that correspond to this region right here. Now, I know the answer. It's 24.2%. Question is, how did I get that? Well, that's actually the focus of the upcoming slides, so stay tuned. We'll get there eventually. For now, just make sure we understand that we're looking for a probability that corresponds to an area under this normal curve. So the question becomes, how do we actually answer probability questions like the one that we just saw when we're not 1, 2, or 3 standard deviations away from the mean? The key here is the position of the value relative to the mean measured in standard deviations. So we'll talk about that in more detail, but that's the idea. We want to measure how far we are away from the mean, and we want to measure that in standard deviations. There's two possible ways for us to do this in this course. The first one is with tables. This will take a lot of time here in this video because we want to explore some of the ideas that are important. And the second one is to use technology. We'll spend less time in this course discussing how to do this because we'll have the ideas in focus, and so the technology will be there just to help us. So what we're going to do here is learn how to use the standard normal table and then how to do some calculations with technology. Before we do any of that, though, we have to talk about how to standardize values. The first step to assessing a probability that's associated with a value is to determine the relative value with respect to all of the other values that random variable can assume. The way we do this is by figuring out how many standard deviations below or above the mean that the given value is. We call this the z-score for that value of the variable. So the z-score is going to tell us, relative to all the values, how far we are from the mean. That's going to be an important concept for us to use quite a bit, actually. Here's an example. The example that we had about the size of adult men's shoes and feet from a previous video. We framed it in terms of Zappos, the online retail store. In that particular situation, for men, the mean foot size was 11 inches and the standard deviation was 1.5 inches. So the question is, how many standard deviations below or above the mean would a foot be if it's 13 inches long? So notice what we're doing here is we're saying, okay, we have a foot that's 13 inches long. We know that the mean is 11, so we know we're 2 inches above the mean. We also know that the standard deviation is 1.5, so we know we're above the mean, and we know that we're a little bit more than 1 standard deviation above the mean. In fact, we are actually 1.33 standard deviations above the mean. We can get that simply by taking the total number of inches we are away from the mean and dividing by the standard deviation. That gives us the z-score for 13. So z is equal to 1.33 when the foot size is 13 inches long. Because the z-score is positive, we know we are above the mean. So we are 1.33 standard deviations above the mean. And this is basically what we just did. We took a formula where we said, take a value that we care about, 13, subtract from it the mean of the random variable, which was 11, and then divide by the standard deviation of that variable. When we do that, we get 2 divided by 1.5, which is 1.33. This formula right here is really important because it tells you how to compute the z-score for a random variable if you know the mean of that variable and the standard deviation. And it's incredibly useful. We can look at all sorts of different data sets. If we wanted to switch to women's foot sizes and we assume that the mean is 9.5 inches and the standard deviation is 1.2, we could then examine how many standard deviations below or above the mean a foot would be, a woman's foot would be, if it were 9 inches long. So if this were the case, according to the calculations below, we can see we would start by taking our value x, which is 9. That's the given foot size that we're exploring. We subtract from that the mean of our data set, and then we divide by the standard deviation. Both these two values right here are given to us in the original problem. Notice this gives us a negative value up on top, negative 0.5. divided by 1.2, and so we get negative 0.417. This z-score, negative 0.417, and its sign tell us that the measurement for this particular foot is 0.417 standard deviations below the mean. We know it's below the mean because this is negative, and we also know it's below the mean because the mean is 9.5. This particular foot's only 9 inches long, and so it's below this value right here. So very straightforward. Let's take a more applied example and begin to explore this a little bit more. This example will also serve us later when we want to start talking about computing probabilities. So remember our example about Gary tires. We had a mean of 36,500 miles, we had a standard deviation of 5,000 miles, and let's say we want to determine how many standard deviations above or below the mean a tire would be if it lasted 40,000 miles. That was the number that we were talking about earlier. You can see here if we apply our z-score formula and we take our x value that's given, 40,000, and we subtract from it the mean of the data set, 36,500, divide that then by our standard deviation, we end up with a z-score of 0.7. So let's take a look at the picture. Let's go back to the picture that we just saw before and add a little bit more detail. You can see here that 40,000 miles is 0.7 standard deviations above the mean. And we know that from our previous slide that 24.2% of those values for that random variable are beyond 0.7 standard deviations. Now, this makes sense. If we think about this, we saw this picture earlier where we talked about looking at the curves from the perspective of the tails, and we know that if we were one standard deviation above the mean, as we see here in this picture over here on the right, then we know that 0.16 or 16% of the values of that random variable live over here in this tail. So if this is 0.7 standard deviations, then a little bit to the right, somewhere around here, would be 1 standard deviation. So to the right of 1 standard deviation, we know there are 16% of the values, and so it makes sense that this whole region here is about 24.2%. Again, we're still wondering how the heck did we get 24.2%, but we're getting there eventually. Again, what we want you to be able to do here is link the idea of standard deviations to the normal curve and link both of those ideas to this notion of probabilities and areas. Now we can finally start talking now about how to actually compute these probabilities. This is a more conventional approach, but it does the job just fine. If you were to look at a traditional statistics book, you'd see tables in the back that describe these numbers that we're going to talk about here. You can actually get a copy of the table at the URL that's listed right here if you want to grab one and print it out. The table is going to help us because it provides probabilities that a standardized normal variable z would take a value less than or equal to a particular z-score. In other words, it gives you the area or the probability to the left of the starting z-score. A picture might be useful here. If you have a z-score like this, let's say, then the table is going to report to you the area to the left of that z-score. So the normal table is always going to tell you the area to the left, and that's important for some of these problems that we're going to see later. A quick note, this table is built on what we call the standard normal curve, where the mean is 0, so the center here is at 0, and the standard deviation is exactly 1. Anytime you're trying to use the standard normal tables that we talk about in this course, you first have to convert whatever value that you have for your random variable to a z-score that has a mean of 0 and a standard deviation of 1. The formula that we've already talked about to do that for the z-score will do that for us, but I just want you to keep in mind that when we're using, the normal tables, we're actually looking at values here on this standard normal distribution. So let's do a quick example using the tables. We want to find the probability that a normal random variable takes a value less than or equal to 0.63 standard deviations above the mean. In other words, the z-score is 0.63. This is what the picture would look like. Over here, you can see that we are roughly at 0.63 standard deviations, and we're looking for the probability that a value would be less than or equal to that, and so we're looking for the area that's shaded to the left, because that corresponds to values that are less than or equal to this z-score. So if I look at the relevant portion of the table, we see a bunch of numbers. We see z-values over here that are in tenths, and then we see hundredths values over here in the columns. So if we want a probability that corresponds to a z-score of 0.63, the first thing we want to do is look at the row that corresponds to 0.6, and that's this row right here. The next thing we do is we move one digit over to the hundredths, and we look at the column that corresponds to that value. And the intersection of that row and that column, this value, is the probability that a value of that random variable will be less than or equal to z equals 0.63. So to sum this up, if we want to answer this question, we could then say that there is a 0.7357 probability, or another way to say that, 73.5% of values for this random variable are below 0.63 standard deviations beyond the mean. We can also do problems where we look at the probability a random variable takes a value that's greater than or equal to some z-score. In this case, z is equal to 1.55, and because it's below the mean, its actual value is negative 1.55. So we're looking for all values that are greater than or equal to this z-score. The picture looks like this. So you can see over here we're between -1 and -2, roughly -1.5 standard deviations below the mean, and so we're looking for all the values that are over here. Now, because of symmetry, we know that this probability should be larger than 50% because it covers more than half of this curve here. So let's use that and verify that. If we look at the relevant portion of the normal curve here, we see we start with -1.5 over here in the first column, which is this row, and then we look to the hundredths column, which is also a 5, and so that corresponds to this column, and then of course the intersection is 0.0606. So our probability is 0.0606. Why so small? We just said that that probability should be greater than 50%. Why is it so small? Well, here's what's happening. The table is giving you this area. If this is -1.55 standard deviations, then the table is always going to give you the area to the left. So this area here is 0.0606 out of a total of 1, which is the entire area under the curve. So the table is always giving you the area to the left. But what you really want is this area, the area on the other side of that z-score of -1.55. So what we want to notice here is that these two areas that you see on the left and on the right, they actually add up to 1. When you add them together, you're going to get all of the area under the curve, which we know is equal to 1. In fact, the area of the graph to the right, which is the probability that z is greater than -1.55, is 1 minus the area on the left. So think about this. The 1 right here represents the area of the entire normal curve. So if I took the area of the entire normal curve and I took away the area right here that's on the left, I took away this little sliver, what would be left would be what you see over here, and that's the one that we want. So to do this computation, all I have to do is take the area that the table gives me, which is 0.0606, and subtract that from the whole area under the curve, and that's going to leave me with 0.9394. Roughly 93.94% of the values should be greater than that z-score, And that makes perfect sense given what we know about the symmetry of the curve. So that's a second example. We need to keep in mind before we move on, like we just said, that the normal table always gives you area to the left. And if you want to find areas to the right then, first you need to find the area to the left of the z-score that you have, and then you subtract that area from 1. So keep that in mind as you do some examples in homework or as we move through the rest of these slides. Let's go back to our tire example. Recall we had our mean of 36,500, we had a standard deviation of 5,000 miles. Let's say we want to find the probability of a tire that will run or that will last for at least 40,000 miles. We've been talking about this example for a while, and we've looked at pictures of this. In a previous slide, we found that the z-score that corresponded to this was 0.7. So what we're really asking here in this question is, what is the probability that our z value is bigger than 0.7? So let's go back to the table and to the pictures that we've been playing with. We know that the probability of z less than 0.7 can come from the table. So if z is 0.7, and because we don't have a hundredths term, we can just go over here to 0 hundredths. We know then that the probability that z is less than 0.7 is about 0.758. And so what that's giving us here is this area to the left, as we've just discussed, of the z-score 0.7. But what we really want is the area to the right. How likely is it that those tires will last more than 40,000 miles? And so just as we saw in the previous example, the way we would get that is we'd start with the entire area of 1, so take the entire area under the curve, take away the blue shaded region, which is 0.758, and what remains then is 0.242. And there you have it. That's exactly how we got the area of 0.242, or a 24.2% probability of a tire lasting more than 40,000 miles. Keep in mind again that in order to get here, we had to convert the 40,000 mile value on one distribution to the standard normal distribution, where the mean is 0 and the standard deviation is 1, because that's the distribution that's represented here in this table that we're getting these values from. Let's move on to a different kind of example now. Comcast, as you probably know, is one of the largest cable TV, internet, and phone companies in the US. Back in 2009, an interruption occurred for customers in Southwest Florida, and as you would imagine, a flood of repair calls came into their call center. Let's assume, after gathering some data, that the mean time of repairs for a customer who called in was 2.5 hours with a standard deviation of 0.75, and that the repair times were randomly distributed. What is the probability that a repair takes between 1 and 2 hours? Now you should notice that this is slightly different than the other questions. So now we're looking at probability situations where we're looking at what is the likelihood that a value is between two given numbers. The distribution that we're interested in here looks like this. And what we want to know is what is the area of this shaded region, because that represents the probability that we care about. On the x-axis here we actually have hours. This is the number of hours for the repair, so you can see here the mean is at 2.5. And we want to know the probability, which is this area, that a repair took between 1 and 2 hours. Again, remember, this is not the standard normal curve. The mean is not 0. And so first what we're going to need to do is find the z-scores that are related to the values that we care about, x equal 1 and x equal 2. So let's let x be our random variable that describes the time of repairs. And we're going to first find z-scores that correspond for x equal 1 hours and x equal 2 hours. Remembering, of course, that our mean is 2.5 and our standard deviation is 0.75. Our formula, as we've seen before, will give us both of these z-scores. When x is 1, you can see the calculations are here. When x is equal to 1, that corresponds to a z-score of -2. And when x is equal to 2, that corresponds to a z-score of negative 0.67. Now here is a visualization of these two curves. On the left you have the distribution of x. This is the number of hours for the repair. We know our mean is 2.5, which we can see here, and our standard deviation is 0.75, and x equal 1 and 2 are labeled here on the left and on the right. After converting to z-scores and therefore to the standard normal curve where the mean is 0, you can see the mean is 0 here, and the standard deviation is 1, you can see now that z equals negative 2 corresponds to x equals 1 hours, z equals negative 0.67 corresponds to x equals 2 hours. And so if you really look at what's happening here, the areas between the two relevant points on the left and the right for each of the two curves, those two areas are going to be the same, and that's because these two distributions are related to each other. So let's go ahead now that we've got to the standard normal curve and we know z-scores, let's go ahead and pull out our tables and see what we get. So for x equal 1, which corresponds to a z-score of negative 2, we can use the table. We see here negative 2.00 corresponds to this cell right here, and so we have a probability of 0.0228. When x is equal to 2, our z-score was negative 0.67, so we'll start with negative 0.6 on the left and then move over to 7 in the hundredths column, giving us a probability of 0.2514. So let's take a look at this in pictures. We have these two probabilities. Right over here, when the z-score is negative 2, the area to the left is 0.0228, and when the z-score is negative 0.67, then our probability is 0.2514. But what we really want is the area between those two z-scores, not either one of these two by themselves. However, let's take a look at what's really happening here. If I take the z-score over here that takes all of this area right here, and we simply remove the smaller probability from that, or subtract it, we get this. We just pull off that area, then we actually get the area that we're actually interested in, and therefore the probability that we want. So in mathematical notation, it's going to look like this. The probability that a repair takes between x equal 1 hours and x equals 2 hours is equivalent to the probability of a z-score being between negative 2 and negative 0.67. We know the probability that z is less than negative 0.67 corresponds to this larger area, that's 0.2514. We got that from the tables. We also know the probability that z is less than negative 2 is 0.0228. And we also just saw that if we simply subtract this smaller wedge from the larger one, what we're going to be left over with is this area here, and that's the one that we care about. And the numerical value then is 0.2286. So let's go back to the original question now that we've got the calculations done. The original question is, what is the probability that a repair takes between 1 and 2 hours? And what we've now done is shown that that probability is 0.2286. Roughly 22.86% of the repairs should be expected to take between 1 and 2 hours. So now let's look at a slightly different example. Suppose that Comcast customer service wants to know how long a repair will take if it is among the worst or the longest 10% of repairs made. In other words, what is the repair time if we find ourselves in this region over here on the normal curve? This region represents the longest 10% of repairs. In other words, this area here is 0.1 out of the entire possible area of 1. So we're here in this region over here on the right. Now, to find this value, to find the number of hours that corresponds to this scenario, we're going to have to start by working with the standard normal distribution. The reason for that is simple. The only tables that we have are related to the standard normal distribution. So keep in mind here that we've now switched to the standard normal curve where our mean is 0 and our standard deviation is 1, as opposed to the previous slide. On the table, what we want to do is find the z-value that gets us as close to 0.9 as possible. Why 0.9? Well, think about it. The z-value that we have here has to give us 10% over here on the right. But the tables themselves only give us areas over to the left. So the area over here to the left that we care about, that's going to give us what we need, corresponds to an area of 0.9. If we can figure out what z-score corresponds to a probability of 0.9, then we also know the z-score that corresponds to this area over here on the right. That's the one we care about. So we go to the tables and we want to find the z-value that gets us as close to 0.9 as possible. And if you look very carefully at the table, there's 3 of them that are relatively close. They're these 3 that are circled. And what you're going to have to do is very carefully look to see which one is closest to the probability value that you're looking for. In this case, since we're looking at 0.9, we need to go here to this one, which is closest to this value. This then corresponds to a z-value of 1.2 with a hundredths value of 8, so a z-value of 1.28. So now we know, if we're back in this picture, let's go back up here to this picture, we know that the z-score that corresponds to the probability that we care about is 1.28 right here on this edge. Now, knowing that, what we can now do is move from the z-value that we've just computed from the tables and use the formula for z-scores to get a value for x on the distribution that we really care about, which is the number of hours of repair. So to do that, we're going to use our formula for z-score that we've been using before, but now we'll use it a little bit differently. We're going to have to fill in what we know. Here's what we know. The z-score is 1.28. The x, the number of hours that corresponds to this, is unknown right now. We don't know what that is. But we still know the mean of that distribution, and we still know the standard deviation of that distribution. And if we put all that into this formula, that leaves us with one unknown. Given that, we can use algebra to solve for that value of x that we care about. So when we do that, when we solve for the value of x, we get an x value of 3.46. Notice all I'm doing here in this first step is multiplying both sides by 0.75. That gets rid of this thing here on the right. When I multiply 0.75 by 1.28, I get this number. Then in this next step, I add 2.5 to both sides of the equation. That eliminates this value here. And over on this side, when I add 2.5 to 0.96, I get 3.46. So, coming back to what we wanted to answer, the worst 10% of repairs we can expect took 3.46 hours or more. Looking at the picture again, here's our z-score of 3.46 on our distribution for x, and this is the region that we care about. So all of these here, 3.46 hours or more, represent the worst 10% of repairs in this scenario. There are limitations to the table. First of all, it can be a little bit cumbersome to use. For example, we have to remember to subtract from 1 if we're trying to compute areas on the right side of our normal curve. We also need to know how and when to subtract for probabilities that correspond to being between 2 values that we care about. And we also need to know how and when to move back and forth between z-values and the random variable values themselves. We've seen examples of that in these scenarios that we talked about earlier. And so whenever you're working with examples such as these, you have to be very careful and you have to think about these ideas that we see here in this list. We've also seen that we're only allowed 2 decimal places of accuracy for z-scores. The table only allows for tenths and hundredths places. So if we need more accuracy than that, the tables aren't always the best bet. And finally, if we are seeking, not seeing, sorry for the typo, if we're seeking a z-value, then the probability that we are interested in may not actually be in the table. We may have to get the closest or the best approximate to the one that we seek, which we just saw in the previous example, and that may have some limitations. Our solution here is to use technology. By using technology, we'll be able to get much more accurate computations for probabilities that are related to normal distribution curves. So that wraps up this particular video. I know it was long, but there's a lot of important information here. And so in the next video, we'll look at how to use technology. But for now, some of the most important ideas of the course have been covered in this particular video. I hope it was useful.